very much for having me. And I should say that this is joint work with Dan Bernstein, who spoke here yesterday, Jonathan Levin, and Boyan Yang. So post-quantum cryptography is something which you have seen at this conference already in several talks and will be seeing more about in other talks. So let me just briefly set the stage with the European perspective. So of course, this has been going on as a research area for a long time, and we've also seen recommendations from different agencies and interest groups. But in the EU, the real big effort started in 2024 when the European Commission published a document with a request for a coordinated implementation roadmap for the transition to post-quantum cryptography, pushing the responsibility on the member states to implement such a roadmap. So to build a roadmap and then to force all of them to do so. This was published at that point with a statement like, hey, come back in 1 year and report what you've done. Do not lose any time. This is urgent. And then later last year in November, there was a joint statement by 17 EU countries, so not all member states, but quite a significant number of them, with the statement securing tomorrow, today, transitioning to post-quantum cryptography. And to highlight some of the parts that were stated in this, they gave a statement that they should, if possible, by the latest at the end of 2030, have transitioned the most critical applications. So 2030, it's October 2025 already, so that's not so long from now. So we really do something, and they're also recommending not to say, oh yeah, we're only moving the most critical ones, but really move everything, including public key infrastructure, at the same time frame. So don't just do encryption, also do PKI, also do signatures and certificates. You remember that in April, the European Commission said, well, come back in a year. They didn't quite manage to do it 1 year later, but in June, they published actually a statement. So there is the NIS2 initiative that's by the member states, and they had a post-quantum cryptography work stream. And well, my slides should be posted already. So there is a coordinated implementation roadmap for the transition to post-quantum cryptography. This is their first version. They were asking for comments by the 29th of September. So sorry, you're now a little bit too late because this is only the first version. They're going to do a more detailed one. But if you're in Europe and you need to figure out, well, when you should transition or how to tell your boss that you need money for the transition, this is the document to go to, because this is now a document by the member states setting a timeline, saying there must be implementation roadmaps by the end of 2026. You must have transitioned important applications by the end of 2030. And then there's also a timeline for the less important ones by 2035. So that means you don't really have time to lean back and go like, well, I let other people do this, but you have to swing into action, and your boss has to swing into action, allocate budget for this. Why is this a problem? There was the store now, decrypt later was a mentioning. So that refers to, well, some agencies. Let me pick a slide from the Snowden archive. So XKeyscore is a program that was exposed by the leaks of Snowden, showing that there are several interception points, all these red dots, and you notice quite a few of those are around Europe. We're in this blob. We are interesting to the NSA. So also other countries are interesting. And that means that all those points capture internet traffic. Now, most internet traffic these days is encrypted. Yay us. Well, 80%, maybe not so yay us. 20% are still not encrypted. But those 80%, they can't break at this moment. But store now, decrypt later means that if they think that this data could be interesting, and well, they might not share the same interest as you. You might think your Netflix movie is interesting. They already have that Netflix movie. They will discard a Netflix movie, but they're much more interested in your emails, maybe even more interested than you are. And those emails all go in this big storage center, say Bluffdale, Utah, where they're going to wait till, well, they have a quantum computer and your emails or other people's emails are interesting enough to be worth decrypting. And the problem is that even with forward secrecy, each connection data has enough information so that if you have all the handshake and then the data, all the handshake and then the bulk of the encryption, you can actually recover it, because in this handshake, you're sending the public keys, which can be broken with a quantum computer. Forward secrecy, very important for the moment, but doesn't help you against quantum computers. So we really need to move ahead and do something. Now for TLS, the situation isn't so bad. This is a screenshot from the Cloudflare radar from when I had to submit the slides. I've just looked before the talk, and we actually now have crossed the 40%. So we're now more at like 45, 46%. The average is shown there as 33.7, so that is taking into account the lower numbers like a year ago. So this is always, the radar is always showing what was there a year ago. And oops, I was trying to point to the slide, not like that. And we've seen a lot of increase. We've also seen some weirdly decreasing numbers. So these are just connections that are captured by Cloudflare. It doesn't capture traffic to my web server, to your web server if you're not in Cloudflare. And we're seeing that at least more and more clients support it. But at the same time, given that 80% of the internet is using HTTPS, there's still 20% which are not even doing the bare minimum. So we can't expect those to move to PostCon TLS. And not everything is solved by having a TLS connection. So can we do more? I know you're thinking, well, yeah, but that means all this effort which is currently going to TLS, I have to replicate across all my applications. And what we were thinking, yeah, that would be bad. So can we do more, but without needing to upgrade every single application? We do not need to do this, or we don't have the capacity to do this for every single application. Can we do like a once and for all migration so that everything helps? So here's a one slide with kind of the elevator pitch for PQConnect. And so one important thing is that we don't need to patch PostCon cryptography onto every existing network protocol, but we add a new layer. So build a tunnel connection that actually protects everything that goes inside. So adding a new layer which has superior security, which is better than what you have at the moment and has PostCon cryptography. We want to build this in a way that can be gradually deployed, and this is something we have with PQConnect, so you can do your part today, and as soon as other parties that you're talking to also support this protocol, you are communicating in a secure manner which has an exit tunnel. So the way that PQConnect is working, and I'll have lots more slides about the details, is that it adds a VPN-like tunnel starting from your laptop, and it goes all the way to the service. And if you're a system administrator, where you have a web page or other services that you're serving, you can install on your server so that every client who is connecting to you automatically builds a tunnel. So the automatic protection, every laptop and server that have PQConnect support actually automatically talk about this because we have a peer discovery built in. All right, so it's designed for security. We have sort of the belt and suspender approach. Everything is hybrid. So we're having long-term identity keys where we're using Curve 2519 as a pre-quantum system. So do not rip out the existing cryptography. This is time-tested and well implemented. And we're adding classic McLeese as a very conservative post-quantum system. So those two, each server has a long-term key. That is defining the identity of the server. We also have per connection data, given the importance of forward secrecy. For connection data, we have an additional Curve 2519 key, which is a pre-quantum again, and we have it matched up with a hybrid in post-quantum cryptography, where we're using Streamline Intro Prime. So that is for the ephemeral keys. And we have also taken this handshake, so the start of the connection, and proven it with the Tamarin verifier. So Dan Bernstein gave a longer talk yesterday about the status of verification, highlighting the importance for verification of the implementation. Tamarin is working at a different level. It's working at the protocol level. And we have shown that this handshake is, well, ensuring that the resulting key is only known to those parties, and that those parties are the parties they think they are. Okay, so this is the one-page advertisement. If this sounds interesting to you, I hope you listen to the rest of the talk. And, well, if this is not what you want to do, at least you know within the first 10 minutes. So, brief excursion, how do VPN works? I mean, I've mentioned this is the VPN-like tunnel. So I assume most of you have seen VPNs from a user perspective. So let me give a little bit more about the technical perspective. So a nice thing, which is why we resorted to think about VPNs, is that they have a big software engineering advantage. You're building a tunnel, and if both parties have this tunnel installed, then everything gets piped through it. Whether this is TLS, which is already encrypted, whether this is you connecting to some HTTPS web page, well, at least your connection to the VPN server is additionally protected. If it's some outdated protocol, say you somehow managed to run Skype still, without getting security updates, but it runs through the tunnel. If you and the Skype server have the tunnel, it would also be protected. So these are applications at consumer side. But if you find yourself in charge of a lab where you still know that, yeah, this lab machine is Windows 98 and we don't have the budget to buy a new one, at least you can put a tunnel right in front of it, so that anybody who is connecting to that machine goes all the way just till before it with a secure tunnel, and then you just have something on-prem where you, well, dealing with the deficiency of Windows 95. Shouldn't happen, I know it happens. So VPN, those cases, is your best bet to do. Now, if you have a post-quantum VPN, then you don't just have extra protection, but you also have extra protection with post-quantum. And you don't have to wait till there's post-quantum support rolled out for your application. So now we're not talking Windows 95 being massively outdated, but we're talking about recently modern applications that just haven't gotten around to adding post-quantum cryptography. So if you have a post-quantum VPN on the same server, then it doesn't matter whether your application is post-quantum secure, you just pipe it through the tunnel. And there are some post-quantum VPNs. So Mulvad, which is a commercial VPN, is supporting post-quantum cryptography for the key exchange. So you're getting an extra secret, or, well, it's a bytecode implementation. So this post-quantum part gives you a pre-shared secret. Then Rosenpass is the endeavor to build a post-quantum VPN, well, basically from similar ingredients. And also if you're using OpenSSH-based VPNs, such as, well, S-Shuttle, then post-quantum is enabled by default since 2022. So since version 9.0, S-Entro Prime, so the same streamlined entry prime that we're using for PQConnect, is supported since version 9.0 back in 22. And also more recently, MLCAN is added as a support. So you can already get VPNs with post-quantum to pipe through. But there's also some disadvantages of VPNs. So the typical usage is that you route traffic to a proxy. When you're using a VPN, unless the data is on the VPN, like in my example of the lab equipment with Windows 95 or right behind it, you're actually just going to the proxy, and then you're still connecting in the clear or with whatever connection safety you have to the endpoint. So it's usually not end-to-end. Another problem is that you're only talking to pre-configured endpoints. You're typically having one VPN configured. Maybe you have two VPNs for work and for some private serving, but you don't have like a VPN to every server on the internet, and it's manually configured. So it's something that is sort of, well, not labor intensive. I'm not trying to exaggerate this, but it's, well, a conscious decision to use a VPN, and you have to turn it on at that moment. So you have to know in advance whom you're going to talk to, and you have to configure this party. So we would like to build a post-quantum VPN, which is end-to-end, so not just to a proxy, and has automatic peer discovery. So that was our ambition in building the PQConnect system. Okay, so like a VPN, we want to protect the network traffic for all applications. So everything should be piped through this. So it should take all application traffic that you have that goes out, and assuming the other end speaks PQConnect, it should apply to it. So we want to have automatic peer discovery to build end-to-end tunnels with a service that's supported. So if you want to install this, as I said, your homework for today, if you want to support this, is to install PQConnect as a client. You just install it on your device, and then automatically you notice if the other side supports this. If you're a server administrator, you install PQConnect, and you also publish an announcement that the server name supports PQConnect. This announcement is published through DNS. So if you're the server administrator, you're also having, well, access to the DNS records where you're saying, hey, connect to this IP address. And in the same interface, you can specify a CNAME, and that's what we're latching on to announce that we have, well, PQConnect support. So on the client side, there is no peer-specific configuration. And also on the server side, you're talking PQConnect to anybody who is connecting to you. There is no per client-specific configuration either. It's for public connections on your network. It's not kind of a registration-based system. You're just willing to build a tunnel to anybody who, well, is interested in that. So this provides application-independent post-quantum protection for every network packet. So typical applications will just run through this, no extra no extra configuration needed. It adds an extra layer to TLS. If you're already using TLS with Postcon, first of all, congratulations, you're ahead of the stack. Cloudflare has these nice high numbers because Cloudflare supports it for all the instances that they're running. If you would be getting a similar data from, well, all over the internet, most servers at this moment are not yet supporting Postcon. So if you, as a server administrator, have already turned on support for Postcon, thank you very much, it's great. But also, well, lots of others haven't, and some of the guidelines are not yet clear. That, for instance, at this moment, there are deployments of MLChem and the deployments of Kyber, where, well, once the TLS spec is really through, then, well, it should only be MLChem. There's backwards compatibility. If you're supporting this, it doesn't mean that people who don't speak PQConnect can't connect to you. So people who don't speak PQConnect, they will not see any difference. People who do speak PQConnect will get this extra benefit. So it adds cryptographic protections in only a positive way. It can even add protections when there is currently none. So if you have some protocol which is not protected or not post-quantum protected, it does help as well. So at the moment, we only have this for GNU Linux. This might be a downer for some of you. So, well, there's always a possibility to install Linux on your laptop, and then you can benefit from Linux and you can benefit from PQConnect. That would be my recommendation. But looking at the server infrastructure, many of the important servers actually run on Linux. So on the server side, it is not a deficiency. It's the typical case. On the client side, we are currently working on ports for macOS, for Android, for iOS, and for Windows. But at the moment, if you want to try it out, sorry, only Linux. All right, so what are you seeing? So what your client is doing, you're discovering the server, you're obtaining the long-term identity keys, and also at the same time, you're obtaining the ephemeral key. So this is one lookup where you're getting the current ephemeral key. So it's a time-based, it's not a connection-based key. So ephemeral seen in the, well, sense of the word, it's temporary. It is a time-based key which you should be using for the next 30 seconds. So it's a rather short time. It will be okay for 2 minutes, but the actual use frame is 30 seconds. Once you have that key, it's a zero round-trip handshake. So that means you're sending data on the first connection. You have all the information that's necessary, long-term key and ephemeral key. It's a purely CAM-based system. And so you can prepare a data package at that moment and send that over encrypted post-quantum, pre-quantum hybrid, and long-term and ephemeral key, all in one packet. All right, at that moment, the client and the server can communicate efficiently through the tunnel. So at that point, the client sends this request, that builds a tunnel between the client and the server. The server then allocates a tunnel for you, and everything gets piped through this. We also have built-in protections against overload and how to resume tunnels, etc. So how does this work internally? I said you have to look up the DNS record anyways. You want to know where the server is. So you're going to DNS, say you want to look up the conference, and you're going to OpenSSL/conference.org, and the DNS lookup, it tells you, oh, we actually have 2 servers for this, pick one round robin, and it only has an A record. At that point, well, OpenSSL conference does not support PQConnect at this moment, so we notice there is no PQConnect support, and we accept the DNS record, and we start a connection with, well, the best we have, which in this case is at least TLS. But if instead you're connecting to our website, so PQConnect.net, in the DNS lookup, you will get not only the IP address, but you're also seeing a blurb here starting with PQ1. So the PQ1 means, well, PQ, it's supporting the PQConnect protocol, and 1, that is the current version number. So if it ever turns out that necessary or advantageous to change to a different version with different crypto primitives, that 1 will move to a 2. So at that point, we are announcing that we are supporting PQConnect on our server, PQConnect.net. And so your client sees, aha, we have post-quantum PQConnect support. We are now rewriting this with a local address. So this is the way that a VPN is normally doing it. So you're writing this to a local address. So, well, I'm giving an example here with 1059, etc. And then this address will actually be the browser's understanding. So your browser wants to connect to PQConnect. it does this dance. The browser then thinks it's talking to 1059, etc. And we are also building a data connection, but protected with PQConnect. We're initiating the session with the actual IP address. And at that moment, yeah, we're sending an accept, and we have a connection builder. Now, connection comes in on this IP address. So, well, the PQConnect, or the normal connection, sees where it comes from. The browser is listening now for the OpenSSL conference. It gets some data from the IP address from, well, one of the two IP addresses from the OpenSSL conference. It's now talking to 10.4.21.44.114, and it's getting data. So that's the normal way that you're expecting your browser to work, and this loads the web page, and we're having a handshake established. For the case of PQConnect, it's now rewritten by the local address. And we're sending get address info, and then we're sending the handshake to the local address. And then it hands over to the PQConnect network to handle the connection going out to the actual IP address. So everything is routed through this. So this is giving you the, well, user application view of PQConnect. Of course, there is a matching server view where they're getting a connection. It is a connection request using the tunnel, so it serves it with a tunnel. Or there might also be a normal user who is not installed PQConnect, and then it serves it like a normal TLS connection. But I want to focus on the ones which are good, so the ones which are using PQConnect. So your connection is now routed through PQConnect. So what does it mean on the cryptography layer? I've already said all the good ingredients that we're putting in. So here's another table showing all these parts. So on the post-quantum side, we have classic McLeese for the long-term keys, and we have streamline entry prime for the ephemeral keys. And for the pre-quantum, we have a long-term X5519 and a ephemeral 2519 key. The motivations for these classic McLeese is the most conservative post-quantum system. It goes back to 1978, so this is a well-aged crypto system in the late 40s. You might have heard of it as having gigantic public keys. That's correct, but remember these are long-term keys, so you only need to look those up just once. And they also have a matching benefit of very small ciphertexts. These are actually the smallest ciphertexts you can get in the post-quantum world. And a ciphertext you have to send for each handshake. So this is a good system for the purpose. A, conservative, this is used for the long-term keys, so you don't want to ever have to change those. And the per connection data is small. Now, of course, X2519 fits into a small corner of everything. It's just 32 bytes. And so we continue using it also just in case we made a mistake. Now, I think the library that we're using there is better than many other cryptographic libraries, but it is still safer to combine it with something where we have time-tested implementations. So we're using X2519 and classic McLeese combined for the long-term keys. And then on the ephemeral side, well, same pre-quantum system, and then streamline entry prime, the same system that I said has been supported in SSH for a long time already. Okay, so that is then, well, required to send a new ciphertext each time, sorry, a new public key each time. And as I said, this is the ephemeral key time-based, so any party contacting the server in the same 30-second window will receive the same entry prime key. This is quite different from how TLS is handling secrecy. So when you look at the TLS design, then yes, it is also forward secret, but it's forward secret on a per connection basis. So, well, if you're having a long-lasting session, if you're logging into your chat system, like you're using Slack or MetaMost or Zulip for your connection on a browser for your discussions, you're actually having a very long-lasting TLS session. I assume you start this when you go to work, or maybe you're even the workaholic who leaves this running 24/7. And that means you're having one session run the whole time. So in principle, this is the same connection. And if you're having somebody with an interception device, well, they would be able to interfere with that, because it's still the same connection as you had yesterday. So if anybody wants to get a warrant from you and they know you're having this connection, they can kick in the door today and they still find something. So, well, that sort of means you are pressured to keep the connection short because it's concerning if you have this long-term session. So that means you have a pressure on the session startup cost. You should not have a long running session. So maybe you shouldn't have your Zulip running for the whole day. Maybe you should connect. And if I'm thinking about my own connection, the internet drops often enough that, yeah, I'm actually connecting. So yay on security, but not so great on session startup cost. In PQConnect, our ephemeral keys are erased after 30 seconds. There's nothing left after 30 seconds that somebody with a warrant could get. Well, okay, it gets erased after 2 minutes, but it's no longer used after 30 seconds. And so another difference is that long-term keys for TLS are signatures. So there's only a protection from the forward secret keys, so only from the ephemeral keys. That's the entire protection on the confidentiality, because the authentication keys do not contribute to the confidentiality. Whereas in PQConnect, well, we have this fast erasure in each session. I'm going to show you the public key part and also the symmetric key part. So really all keying information is gone within 2 minutes. And the long-term keys are CAN keys, which means they provide at the same time authentication and encryption. So you're sure that when you're talking to a PQConnect server, the server is live at the moment, it is engaged in a discussion with you, so it's not a pre-recorded message. And it is also using this extra protection for the encryption. So encryption has sort of more layers than if you would be using TLS. Well, CAN TLS, of course, has the same, but normal TLS doesn't. So I already mentioned the long-term key view. So on the connection establishment, you're downloading the long-term keys for the identity. You are making a packet. This is a MAC-Lease 6960 key. And the public key is rather large. This is the megabyte thing. So this is much more than a DNS packet. So we do need to get this via the DNS lookup to the client. And so what the DNS lookup actually gets us is a hash of the key. It's not getting us the key itself, but it tells us, okay, this server is supporting PQConnect. Now talk to the server and get the key. So the long-term key is distributed with a Merkle tree. So it's in packet-sized chunks. I have a picture of that. So the leaves of the Merkle tree, we're just having like small pieces that can be looked up in one packet, and we're publishing the root of the tree as a DNS. So the client requests this tree packet by packet, and as they go up, they can actually verify that this is correct. So here's this picture. So at the bottom side, you're seeing the pieces. So PK0, PK15, etc., 35, etc. So these are the pieces of the MAC-Lease key which hash in there. So the first hash going up the tree is from 0 till 35, and then the next one is from 36 till 71, etc. And at the very far on the very far right end, you have a tiny elliptic curve key, which is also hashed in there. So all of these get hashed together up the tree to this piece, this H00. So it's a 0th level, and there's only one key, so that's H00. That is the one we publish in DNS. All the other pieces get looked up, and you're also asking for the next package up in order to verify that you have received everything correctly. So this is how we get the long-term keys from the server to the client. So at the moment, each server is also a key server. So at the moment, each server is issuing these keys upon request. But the long-term key doesn't change, so only you need to do this dance once. You do need to look up the ephemeral key when you're coming back, but you don't need to look up the long-term key. We're also doing some interesting things because, you know, where do I have to store a megabyte for each of the servers that you want to talk to? And the answer is no. We're actually fetching the key once, and we're pre-computing ciphertext to those. So we're only storing the small ciphertexts rather than the large public keys. But that's a minor detail. Then on the ephemeral key, well, we're also using the same lookup mechanism. Now the ephemeral key is rotating, and this is also much smaller. This is on the kilobyte size. And so, and so we're now doing a lookup to the server saying, okay, I would like to have the current Streamline Intro Prime key and the current X2519 key. So those together fit into a single UDP packet, And so the client just requests this packet from the server before sending a handshake message. So this is what you do for each new connection to the server. The long-term key you do once for the server. Of course, if it's a new server, you have to do it. But if it's a server you're talking to regularly, like your work server or Gmail or whatever it is, then you're doing only this part, and these keys rotate every 30 seconds. There's a multi-use, but it's a short lifespan. So any warrant, well, that would have to be very fast to get within the 30 seconds, because it still accepts it for another 90 seconds, so 120 seconds in total, 2 minutes, but then the key is erased. So the private key is completely erased. There's no trace of it, so no way to discover it from the ephemeral key side, so from the private key. Of course, if you made a bad choice and the system is broken, then of course, also here ephemeral keys don't save you, but at least for what we know, this is a secure post-quantum system, it's a secure pre-quantum system, so they're doing what they're supposed to do, and then the only concern is that somebody would come with a warrant and say, well, give me your current key material, and then, well, 120 seconds we believe is short enough to be fine for most paranoia levels. Okay, so we have these combination of these keys, and then these handshakes are doing a secret, well, a CAN secret against all 4 public keys. So we're doing this computation on the client, so there is now one key which is getting the benefit of all those 4 keys. I have a picture on the next slide showing the layering of this. Now, this handshake message M is then protected with all of those, so when the server receives the handshake message, they have to do a bunch of computations against each of the public keys to eventually get the same handshake secret, and then they can decapsulate, or they can decrypt the payload. So this is a hybrid approach, both in long-term and ephemeral, and in pre-quantum and post-quantum. So each public key layer is inside of the next one. So here's this nesting picture that I like to show. So we have the McLeese on the outside, because this is a post-quantum system, and it's, well, our understanding is it's very secure, it's very conservative. So in this case, it protects everything, including the curve 2519 key. So even if your attacker comes now with a brilliant quantum computer which can break curve 2519 keys instantly, and they're seeing the long-term and the ephemeral curve 2519 key, they don't actually know what ephemeral key the client sent, because that's already protected inside the McLeese layer. So we're starting with the McLeese encapsulation that gives us a shared key, and then we already encrypt the curve 2519 ephemeral key to that decapsulation key. So at that moment, that key is not visible to the attacker. So unless we all missed something for the last 40 plus years, they can't even get to the curve 2519 key. Then we have another curve 2519 layer, which is ephemeral, so that's the short-term key from the server, and then inside we have the streamline entry prime. You might have heard me saying that, well, lattices I trust less, and yeah, that's also part of this design. We're putting this on the inner layer so it is protected from the other ones, so attackers do not see the streamline entry prime key. To get to the attack that they would need to do on the lattice-based system, they would have to peel off all the other layers. So going back to this overview here, so each public key layer is inside the next one. So it forces a sequential attack. You really have to do the outer one first. So it's like peeling the onion. I don't want to say this because then people think of like onion routing or something, but this is really a similar layered approach, but in this case, it's not different nodes, it is different crypto systems. And so we're keeping the assurance from the X2519 key exchange. So this is the pre-quantum one, which is state-of-the-art, and we will not do worse than that. And you might go like, well, this thing is kind of complicated. Are you sure that all your messages and decapsulations, etc. here are fine? So there, this is the part that we were proving with the Tamarin prover. So we have a proof that this concoction, which is doing, basically, well, it's doing 4 key exchanges, and each key exchange is encrypted with whatever we have built up so far. So this is sort of like in the noise framework that Signal is using. As soon as you have a shared key, using it to encrypt the next part, except for it's not on the next message, it's all within one single handshake. All right, so much on the public key cryptography. Now, I've been ranting against TLS having these long-lasting connections. And so I should also talk about the symmetric key. So at the end of this, we have a shared symmetric key. At that moment, the client forgets all the pieces of the public key cryptography that they have put in. So what they used for the MAC-Lease encapsulation, what they used for the ephemeral key in the Curve 2019 encryption, and what they used as ephemeral what they used as the chem key for the enterprise. So those are gone. So even if there's now a break-in, the attacker wouldn't get that anymore. So there's now the starting key, like the root of the symmetric session. And at that moment, we still have the promise to the user that everything gets erased within 2 minutes. So there should not be a key in use for more than 2 minutes is our promise. So everything has to be erased. Now, we also want to have unique packets, unique keys per packet, because that means that if we're having an assignment of packets to keys, any key that has been used can be safely erased by both parties. And if there's a packet which was transmitted out of order, delayed by some reason, you only keep that key and then not the next one. Now, of course, there must be a way to derive these keys from the root that we just computed on both sides. So I need to ensure that if I'm keeping that key while deleting the next one, that you can't just recompute it that way. So I can't just have a ratchet going linearly this way if I want to make sure that there is no recovery possible from what I have on my data. So if you want to deal with delays and drop packages or reordered packages, we need to have per packet keys, and we need to have a way that the packet keys are not directly dependent on one another. So we designed a new ratchet for this. I already argued about the 2 minutes. And so when you're used a key, you definitely want to delete it. And also when you received something, you delete it. But also whenever the time passes 2 minutes, you also delete it. So those are the requirements that we put onto our ratchet. And so here is the one slide with how this looks like. And I'm going to go through this in more detail in a moment. So the starting key, so the root of this whole thing, the E0 is the initial epoch key. So we call this epoch keys because they advance every 30 seconds, there's a new epoch. So going down vertically, we have epochs E0, E1, E2. And so those epoch keys are directly related to the initial root that we get from the PQConnect handshake. And then we're hashing forward, going down from E0 to E1 to E2, etc. So these are the epoch keys. And then I was already arguing that we want packet keys and that they should not be directly related to one another. So if I have a packet key 01, it's in the first epoch, and it's the first message in there, I should not be able to go to the second one because I might have the first one delayed. And so we're having an extra hash operation. So there's a chain going down. So these are the chain keys. These are the C, and then the first index is the epoch, and the second index is the position in the chain. And then each of those has a little pendant hanging down. Each of those has the packet key. And so each epoch is every 30 seconds. Keys are erased at least after 2 minutes. And having these hanging down packet keys means that we can safely erase P02 and keep P01 in a way that, well, you couldn't recover P02 from that. Now, when we were building this thing, we're like, okay, this looks like half a Christmas tree with all the pieces hanging down. This is like the Christmas tree you build if you're in a half attic. So anyway, so this Christmas tree picture is what I'm going to talk over the next few minutes, and then we still have some time for questions. Okay, so we're starting at the beginning of it. So we just finished the handshake. It's time 0 seconds, and we have E0. So at this point, we haven't received any packets, and so we're starting off. The first thing we do is we hash this E0 forward, both on the chain key and on the epoch key. At that moment, E0 has been used. There is no more need for E0, so we can erase it. So E0 was rather short-lived, and now C00 we need for 2 things. We need to go further down the chain, and we need to get the packet key. So we're doing that, and then we can also get rid of C00. We still haven't received any packet, so, well, we can pre-compute some more, but now the first packet comes in, P0, so we're using our first packet key, lowercase p000, for the received packet, so it's 1 second in, and we have received a packet, so at that moment we can erase this, well, we use and then erase it, and we also know the next one will be coming, so we pre-compute the next packet key, and we compute the chain key further down. If everything is fine, the next packet arrives in order, so we're doing the further things, etc. So time goes on, we now have reached 115 seconds, and finally another packet comes in. Oh, this is already in the 2 chains, so something has happened. We have missed a whole bunch of packets, so we're already 2 chains down. So, okay, advance the epoch, get to 2. That would have happened at 30 seconds in, so at 60 seconds anyway, but also we're now going down the chain in here, and begin down the chain in here. And we now have this P21 packet key, which we'll now use and erase. We still have the possibility to receive messages and packets on the first 2 epochs. So you're still seeing some blue keys up there. So only after 2 minutes, after 120 seconds, we're, oh, okay, now it's a delayed packet, sorry, I forgot about that. That packet comes in, so we're using that key. And now after 2 minutes, we're finally getting to the part that the whole upper thing is erased. So at that moment, the packet keys, whether used or not, will be erased. If anything comes more than 2 minutes delayed, sorry, this is our trade-off between usability and security. Our cutoff was at 2 minutes. If you're living in a country where you're going through tunnels with your train for more than 2 minutes, you might not be happy with our choice, but it was the choice we felt was the right thing for our paranoia. Okay, so further on, you would be building more epochs. So if now packet 02 comes in, sorry, it's too late. This can't be decrypted anymore. So the underlying microlibraries, very small pitch. So we're using existing libraries which have received some audit. They're also packaged for Debian, so we can just do install easily. So there's the MacLeese microlibrary and libmacLeese. There's a lib2519, and there's a libentropprime. So these are used for the crypto systems. They are written in C with assembly, and, well, they're easy to use from other languages, so we are wrapping those. At the moment, our published implementation is the Python implementation, but all the crypto specific tasks are handled by these microlibraries, so they are actually pretty fast. It's just the connection handling that is still in Python, and we're currently working on Rust implementation. So we have extensively tested these libraries, and there's optimizations and protect against timing attacks, etc. Not quite at the level that Dan was presenting yesterday for the S2N Bignum, but these libraries are ones where we felt, okay, this is the best in business for PostQuant. Okay, so to install, if you're on Debian, it's just sudo apt install. There is a packet for PQConnect on the server. It's pqconnect.server. On the client, it's just PQConnect. On the other OSs, we have web pages which tell you what to do, how to install it. So pqconnect.net is our web page, and you're finding more information there for users and for system administrators. So if you actually like this talk, it's easy to install. Let me briefly jump ahead to the last slide. If you did like this talk, here's a full paper published at the NDSS this year. So the paper is online. We have more information on the web page. We also have a Zulu chat where you can discuss your feature requests and get updates. And we also have an awesome logo. This is a pangolin, which is an animal native to Asia. And in Chinese, it is an animal that digs through walls, which we found very suitable for something which builds tunnels. So with that, I'd like to thank you for your attention, and I'll be happy to receive questions.
If my application sits in a container staring down at the OS.
To hear the question. Is it possible to speak louder?
I'm almost swallowing the mic. All right, very slow. Can you put the choice of your algorithms in the context of crypto agility? And the second question is, if the application sits in a container staring down at the OS, how much trust does the application have into the OS? Thank you.
Okay, so let me comment on the agility first, like the crypto choices. So these are implement with libraries. I commented that we have a version number. So there is no negotiation phase. It is an opinionated system because we think that if you have a negotiation phase, that adds fragility to the program, and we do not want to have downgrade attacks ever. So you're either advertising a PQConnect 1 key or you're advertising a PQConnect 2 key. I mean, you would be then, if we have a second version, advertising that you have that key, and then the client picks which one they speak. It's not a on-the-fly negotiation. The protocol is designed with CAMs, so you couldn't just change it to signatures. In principle, you could change the CAMs, so if it turns out that Streamline Interprime or all lattice-based systems are broken, we can put something else in there as a ephemeral key. Of course, there are differences on the sizes. I was highlighting here, or this will be difficult to go back to. I was highlighting here that things fit into a packet, so we would need for the ephemeral key there we go. So for the ephemeral keys, well, the elliptic curve, that's the typical size from elliptic curve. For the Streamline Interprime, if you're going away from lattices, you're typically running into problems that, well, if you go into other lattice-based systems, you might be running into problems there on the ciphertext size. So this is a size that works for structured lattices. This could work for MLCAM as well. It wouldn't work for Frodo, for instance. So the public key size and also the ephemeral ciphertext size are defining features. So there are limits to what we have flexibility, but okay, if all lattice-based systems or all structured lattice-based systems are broken, then this inner layer would have to be changed. So then this part where the Streamline Interprime is there would be replaced by something. At the same time, at least we would feel comfortable not having exposed any user secrets because it's the one which is most encapsulated. It's all the way in the inside. I'm having a lot higher confidence in the MacLeese system, so I'll be really surprised if something happened to that. And so we're putting that on the outside as a choice that we're really comfortable with. And I would need to see quite some strong arguments to deviate from that because it's really convenient for the small ciphertexts, and it's yeah, also very conservative from the security assumption. How much trust do we put into the operating system? Well, so at this point, operating system you still, of course, need for random number generation. That's a general issue with cryptography, that if the RNG is broken or hacked or something, then you have a problem. There is some part in the PQConnect that we are rerouting the messages. So we're going, it's not in the kernel, but we're still intercepting all the messages and rewriting them. So this is like a VPN works. So there is some hacking in the system. It goes pretty deep in there. So maybe the question should be more, how much do you trust our implementation there? At the moment, it's maybe better because it's only Python, so easier to audit. But on the other hand, for the performance, this will be rewritten in Rust. I'm not sure I got the full depth of your question regarding trust to the operating system, but I hope this answers some part of it.
One more question here.
Can an edge machine running this software protect a LAN of machines behind it?
Yeah, so the example I was giving of a VPN protecting a Windows 95 lab equipment. So it only, of course, goes to the endpoint. So if there's still a possibility for somebody to attack the part between kind of the PQConnect server and that lab equipment, you're still in that trouble. But if you're putting those on-prem and you have firewalls or whatever, then yes, that should be a good use case. It's something where we're talking with, one of our authors is with Academia Sinica, and we talked with them that, yeah, some departments have all the lab equipment, and that is running the program which is relevant, and so they can't easily change it. And so this is one of the use cases we see for PQConnect, that you put this as kind of a box in front of it, the way you would normally put a VPN, except for it is, well, easy to configure, it doesn't require per client configuration, etc. And so yes, that's one possibility. We prefer, of course, to go fully end-to-end, so it would be best if you have this on your endpoint, but of course, we're not going to give you Windows 95 compatible software, because I think if you have a Windows 95 computer, then you're also in problem with running a modern Python.